Yeah, so thanks for coming to our session, which is going to be about sharding strategy, best practices, and situations and places where it's not so easy to implement the best practices. And if you run into such a situation, what can you do about it, which is basically the title of the talk, Dynamic Sharding Strategy, followed by solution implementation. Yeah. So before we talk about the problem statement, just to establish the sharding strategy best practices. So I usually look at three things for sharding strategy best practices: the size of the shard, the distribution, and the replication factor. Yeah. For the size, on paper the recommendation is anywhere between 10 gig to 50 gig shard size is good. But whenever I say this, the first follow-up question that I get is, this is a really wide range. Can you be a bit more specific about it? Yeah. So the specific answer, usually the go-to answer that I give is, so if you're dealing with e-commerce search, for example, if your workload is e-commerce or retail search, where the search latency is super low, super critical, super stringent, right? But also the data set is not too huge, relatively speaking. So you're probably dealing with maybe 100 gig of data, unless you're Amazon or eBay or Alibaba. Yeah. So those times you look at the lower end of the range, around the 10 gig mark. Yeah. Versus if you're working on a log analytics use case, where you have tons and tons of data, terabytes and petabytes. Yeah. But then your search latency, I mean, it is still critical, it is still low, but it is not as stringent as in an e-commerce search, for example. Yeah. So those are the places where you look at the higher end of the range for the shard size. Yeah. So anything that ranges in between, so it's basically the amount of data that you have overall on your search latency, the criticality. That determines the optimal shard size between this big range. Yeah. The second thing is the distribution. Yeah. So for distribution, I usually keep it very simple. Distribute it on all the nodes that you have, all the data nodes that you have for a given index. Like in this example, where I have the Apple index, let's say of size 30 gig index size. Yeah. So if you were to do with those two best practices that we just discussed, right? Size would be 10 on each node and distributed on all the available 3 nodes. Yeah. So it's easy. Yeah. But let's say we have an orange index, and let's say the index size is around 22, 23 gig, right? So now, would you compromise on the shard size best practices and distribute it on all the 3 nodes, or would you compromise on the distribution and have at least a minimum shard size of 10? Yeah. The answer is quite difficult to say. It depends, right? But in this case, it's quite easy to answer. I wouldn't do something like this, because this is going to create a node hotspot. As you can clearly see, 3, but you have 4. And also the size of each of the shard is quite different, making this node a hotspot. Yeah. So, but like I said, in here, answering it is quite easy. But when it comes to reality, when you have a multi-tenant workload where you have a lot of index families, index pattern as we call it, right? It is not easy to design something on paper and implement it because it's very chaotic. Yeah. So, which brings me to the problem statement. Yeah. So let's say you are a platform team. Probably you are. Yeah. And you are responsible for running and operating OpenSearch. And a lot of application team in your organization are sending in logs in every possible direction. Yeah. So now, sooner or later, you're going to run into performance problem. Yeah. So they're treating your OpenSearch as a SaaS solution for their observability, but you know the pain because you're going to run into performance problem when you do not manage it and when you leave everything to the defaults. Yeah. So the first thing that you probably will do is take a look at the key resource metrics, CPU, JVM, disk throttling, so on and so forth. Yeah. So as an example, I cannot show every metric as an example, so I'm going to show CPU as an example because it's quite easy to quantify it. Yeah. And I have two different examples here, or rather one in different perspective. Yeah. One is the top one being a cluster level CPU metric, which has the min, max, and the average. The second one being at the node level. Yeah. So as you see here, right, let's zoom into just this particular point. It's easy to discuss that, right? So certainly it looks like one or two nodes are acting up really high, while the rest of the nodes during that time frame barely doing anything, looking at the average and the min. Yeah. The next thing that you do is you zoom in at the node level. You probably see something like this. Few nodes go up with CPU, hitting the max. Yeah. They go down. Few more nodes go up. They go down. And I mean, this is a 3-week chart, but depending upon what time frame you look at, you're still going to see something like this. Yeah. So I am in a customer-facing role, and usually this is around the time when I'm involved. Yeah. So this is when I'm called. So, and the first thing that I look at, or one of the first things that I look at, is the sharding strategy. I look at the shards and see how well they are, go through all the best practices I just spoke about, yeah. And then, naturally, the first thing that I say is, all the things that I told you, I'm going to tell them, hey, these are the best practices. I basically preach, yeah. And to my surprise, they tell me they know all about it. Then the first question is, hey, if you know all about it, why did you not implement it in the first place? And that is when they say it's easier said than done. Because like I said on the previous slide, you know how we can easily say, hey, I will rather do it the other way, right? Distribute it on all the 3 nodes, yeah? But when it comes to practicality, it's not easy because it's chaos. Utter chaos when you have one of the customer that we dealt with, which is what this was based on, had about 50 different index families. And you can see 50 different index families from all different sizes, high volume, low volume, mid volume, yeah. So it's not, basically it's not easy to implement them. To expand on the same thing, the biggest problem why it is not easy to implement is also the fluctuating ingestion rate and the search rate, right? We or you as a platform team are not able to determine or predict what the ingestion rate and the search rate is going to be for the future in order to preemptively make sharding strategy. Yeah? You probably think it's the application team's responsibility to tell you in advance when the traffic pattern changes so that you can adjust the sharding strategy. But let's say even if the application team comes and tells you in advance that something is going to change, right? What if 10 different application teams coming at the same time telling you, hey, we have this is the amount of traffic pattern that changes. So this is once again a lot of homework for you. You have to now go back to the paper, do the design for the sharding strategy, implement them. A lot of manual work, overwhelming, out of control. Yeah. So to take some examples, I'm only having ingestion rate in this example, but search rate also has the same problem. Yeah. So let's say I have 4 different examples here, 1, 2, 3, 4, yeah. If your ingestion pattern is something like this, the top nice wave, right? Very predictable pattern. Do the sharding strategy on paper, implement it, everyone is happy. If your ingestion pattern is like 2, there is still a pattern to it. There is still something that you can design on paper, implement it. It's just that you have to change your thing every once in a while, but it's still manageable, yeah? But let's say if your ingestion pattern is anywhere like 3 or 4, no clear pattern, nobody is going to tell you when things are going to change. What are you going to do about it, yeah? So, like I said, the search pattern is also the same problem. If I have to bring that also into the mix, it's not going to be easy for me to explain it, so I'm just going to stick with the ingestion pattern alone, yeah? But trust me, bro, search pattern also has the same problem, yeah? So enter dynamic sharding strategy, which is the solution that we came up with. And before we walk through the actual solution, I also want to tell you where this can be helpful. So when you have a fluctuating ingestion traffic, right, It is usually not a problem if you are doing a rollover based on size. If you're doing an index rollover based on size, it's usually not a problem because sooner or later you're going to hit your optimal shard size. Let's say it's 50 gig. Sooner or later you're going to hit it, right? But then if you do a size-based rollover, but if your retention period is too short, let's say there are times where we see retention period to move to warm and cold, right? So to warm, maybe 30 days, 45 days, no problem. Yeah? One way or the other, you're going to hit the optimal size. But then if your retention period is 24 hours, 36 hours, and trust me, we have seen customers having retention period as low as 8 hours. Yeah? So there is hardly, there is a very good chance that you're not going to hit the shard size before the time runs out. And when the time runs out, what happens? You're going to produce differently sized shard, too many fragmentation. The same node is going to have different sized shard, leading to storage skewness, which is once again going to lead to the CPU chart that you just saw. Yeah? So these are the inherited problem, yeah, which this we think is going to solve. Something that we implemented for one of our customers. So basically it goes like this. As the title says, a very minimalistic approach just by using the OpenSearch API. Nothing fancy, straightforward. And what we do is we run the cat indices on the hot. And this example is for the Amazon managed service. I'll tell you for the OpenSearch later. Yeah. Run the cat indices, get the previous rollovers. And when you do hot, you basically are looking for only the data that exists in your hot tier. Let's say if your retention period is 8 hours, right? All the data that's there for the last 8 hours, yeah? Including the size, the primary store size of the index. And then what you do is, based on this, so you assume what you have for the last 8 hours is going to be continuing, more or less, right? And this is going to be your data point for predicting, or this is going to be a data point for identifying what is going to be your next rollover's shard size, or the shard count, yeah? And the optimal shard size is something that you already have for the given index, yeah? And then, quite simple, we do a get index template. You get the current indexes template, update the new finding, the new shard count, put it back, yeah? And then the new sharding is in place. So basically, if you look at it, what we are doing is we are looking at historical data, but not too much in the past. Only those data that is there in the current hot tier. Hot probably is going to be, not probably, is only going to be the data that is in your current retention period, yeah? So, and you, everything, all this prediction or the logic that you would write right now is going to exist outside of OpenSearch. Let's say you run a Lambda or a batch job if you're running self-managed, yeah? Identifying all those things, pretty simple because it's just using cat indices, yeah? Nothing fancy. It's just that you have to have some calculations which will come later, So you identify and you implement it and you run the batch job every 5 minutes is because ISM runs every 5 minutes by default. If you change the default to, let's say, 10 minutes, then you can also run this batch job every 10 minutes to find the new set of primary shard size, yeah? So just to give you an example, this is how it looks like. Hopefully it is visible because of the dark screen. So the cat indices, this is how it looks like, right? So what we do is we get, if you look at the column H, right? These are the columns that we asked for, yeah? I mean, you can ask for more, but this is what we need, the bare minimum. The name of the index, the creation date, and the primary store size. So it's basically going to list something like this, yeah? So I will not go into the details of this because Robert is going to, he has a better way of explaining it, so he will explain it. But basically, this is what we get back. And the creation date is going to tell us the primary store size, and the creation date is going to tell us for how long, how much has been filled up. So this is the data point that you use for your next iteration, yeah? So I told you that this is just for the managed service or the Amazon managed service, and that is because, silly me, I thought _hot will also work in the open source or the self-managed, or if you run it anywhere else. It's only last week I realized that this is, like I said, it's not applicable for self-managed, right? But you can, you can still use the list indices. List indices is relatively new. I think 2.17 or 2.18 is when we released it. And the good thing about list indices is it also supports pagination. So I mean, if you have in a log analytics use case, if you hit it right, you have 10,000 indices, right? You cannot, you do not want everything in one go. So this is where you can use the pagination. It goes something like this. You can look up the APIs, and you can look at the size. And you can also say, instead of doing everything in one go, you can also say index by index, just get the Apple index, or just get the orange index. Use the creation date as the cutoff time for your retention period, right? And then you get the data point that you need. Yeah. So I will pass it on to you now to explain the.
Thank you, Aswath. So Aswath told you I have a better way now to explain how we use that data. So my better way is basically a bunch of PowerPoint animations. So stick with me here. Just to reiterate, as Aswath said, there's many ways to make this solution more sophisticated. There's many dials and knobs, how you could tune it and how you can think about it. And we will discuss this a little bit later. But keep in mind, what I present was like the bare minimum version we implemented at the customer. And the context was basically we wanted to get something out very quick and something that's still simple, that works and is understandable for the customer. And as Aswath said, we really try to build it in a way that it's just basically a stateless cron job. So it just interacts with the OpenSearch API. It pulls the data that Aswath showed before, makes some decisions based on that, and then manipulates your ISM policy templates that then will get active at some point in time. So the benefit of that was for us really that we didn't need to have an additional data store, right? So we didn't have to collect any additional metrics. We could just use what is basically provided out of the box from the OpenSearch API. So the way you can think about it is this way. Let's say we have our index here, and at some point it was created, or it has already been rolled over. And every time we create a new index, right, we saw that we have a date when that happened. So that's one data point we can use. And then you can imagine this index grows over time, maybe to 100 gigabyte or to something else, doesn't really matter. And then it rolls over again, might be because of an ISM policy. So we get another data point because we know that at this point in time, a new index is created and we have another timestamp. So that at least gives us a very coarse, like very high-level view of, okay, how much time has passed between that, how much gigabytes have been produced in that index. And we will use that data to make some predictions. So this might go on, and at some point, we actually might be in the present. So we can look back at that data that we get from the API and see like a few states and timestamps and see how the index has grown in that time. What can we use it for? Well, obviously, we know what time it is now, for example, when the script runs. We can look back at a bunch of those timestamps and see what was the total primary storage size that was accumulated in that time. And then also, we know the timestamp when it all started, or whatever timestamp of those, you could also take less. It goes back into the past. And with that data, we can basically do a very simplistic way on figuring out what could be the potential index growth. So very complex formula, right? Essentially, we try to calculate the average growth over that time. So we take whatever timestamps we have, we accumulate the storage size that we have accumulated there, and we take the time, so the period that we had between those steps. And if we have that, coming back to the retention period that Aswath talked about, when we want to have the best of both worlds, so we obviously want to scale out the shard number, but we also want to hit an ideal shard size, we can basically multiply that with whatever retention period the customer has set. So in our case, the customer basically set this to 30 hours, so we knew ideally if the index would continue to grow on average like this, after 30 hours, we have this and that accumulated primary index size. So maybe a few hundred gigabytes. Now the final step is obviously to determine the shard count for that potential growth. And what we did here is basically, it's a few if-else statements, and you can do this differently, but basically we created a few brackets that say things like, well, if we predict that this is a super, super small index, no velocity, maybe it's development, it's testing, whatever, it doesn't really matter. If it's below 10 gigabytes, just use one shard, it's fine. If it's between 10 and 30, do 2 shards. If it's between 30 and 60, do 3 shards. And then everything above that, so above 60, we basically just take the predicted total size and divide it by our ideal shard size, so in this case, 30 gigabytes. And as Aswath said, you can obviously play with that number, so you can say 30, 40, or 50, and that's already one of the dials and knobs you have here, right? 30 is on the lower end, so you can already see it would more aggressively shard out here, which might be what the customer wants for their spiky log ingestion. And then basically the last line, I think we could have formulated that better. It just says we will not go above the number of nodes as the maximum shard count. So even if it would determine, well, it's 15 shards and you only have a 12 shard cluster, at least for now, we would clamp it there. And again, this is something you could basically manipulate, change, depending on your needs. Now let's make an example for that exact picture. So some very simple math here, right? We basically take the whole period that we can see in the OpenSearch API. We see in total that's 250 gigabytes from 20 hours ago up to now. So we divide this by 20 hours, and we say, well, on average, that index is growing 12.5 gigabytes per hour. And then we take that growth, and we multiply it by the retention time. So we're saying, well, we think in 30 hours, this will be like 375 gigabytes. So what's the ideal shard count for that? And I'm not showing the brackets here, but essentially, because it's a rather large index, we just divide by 30 and we come out at something like 13 shards. And that's actually what the script would then write back into the ISM policy. And that's what the script would do on a continuous basis, because as the index keeps growing, right, this can change the average potentially. So whenever the ISM policy actually hits and rolls over the index, we kind of take the latest value that we have computed for the number of shards it should have. So what did that give to our customers? So we implemented this for a large sports brand, which obviously has a lot of spikes in their applications, you know, for certain events, Black Friday, these kinds of things. And this was a logging system. And in the past, they tried to manually, as Aswath said, manually try to guess what teams need, try to communicate with teams, but it wasn't really working out so well. So for them, that helped them a lot. One of the things that immediately happened is that, in general, their users reported a better user experience, obviously, because now, more or less automatically, within the retention period, sometimes earlier. Basically, the shard count was more well aligned to the actual index growth. So obviously, this helps with latency and performance because you're better utilizing the nodes of your cluster. Now, they also saw this higher elasticity in staging environments, so I already alluded to that. Obviously, that doesn't just scale out, it also scales in. So after a day or two, when suddenly your testing is over, you're not doing anything anymore, it also goes back to fewer shards, so that gives you a more realistic view on your whole cluster, on how many shards you have there and what you need the capacity for. And in general, they had less configuration work. So as I said, this whole guessing thing basically went away. And typically what they see is like if you have some recurring pattern, some average usage that would basically go into effect within the retention period. So once it rolls over, right, the shard count is updated, and it could then also update in the future to different values. And as Aswath said, because you typically would use this together with a size-based rollover, if the index is suddenly growing faster, the benefit is actually that when it rolls over, you still have the optimal shard sizes for the index you just closed, you just finished, and you would even earlier get the reaction on having more shards, right? Because the index filled up, it did that faster than before, and then it would apply a different shard count. So if suddenly the index starts growing very fast, you get a faster reaction from this automation. So overall, that was very helpful for them, because although it's very simple, it helped them to have a better baseline and also a lot of cost savings. So if you remember the spikes Aswath showed in the beginning, that was really because those shard counts weren't really well aligned, and that helped them to smooth out this graph, because in general the indexes were better distributed over the nodes. Now, I'm not saying this is solving all your problems, right? Because that's the next thing we need to talk about. Obviously, this is a very simple solution to get started, and we're still living in the, let's say, in the laws of OpenSearch physics. So obviously, there are still some things that could be better here. So obviously, with any kind of scaling, and that's not really specific to OpenSearch, there are a bunch of problems or things you need to consider. So one of them is obviously the prediction algorithm, or essentially the question, what am I scaling to? What's actually my scaling target? And I showed you here that we took a very simple approach to that. We just said, look at historical data and create the average growth out of that. But of course, you can apply different calculations here. As I said in the beginning, you might actually use a system to store metrics of many snapshots in between, so that you can actually see how the index grows between those rollovers. We don't have that data because the API will only give us these discrete timestamps between rollovers. But obviously, you could just regularly query the API and gather more data and use that data to, for example, figure out that there are some higher peaks than the average we predicted. And for your use case, you might make the decision that actually you want to go with a growth rate of those peaks and not just the average. So there's a lot of room to play here with what am I actually scaling for? The other thing is the scaling behavior itself. So if you answered, okay, what am I scaling for? What's the target metric? The next question is, how do I react to that? And you saw in our case, we decided, well, we have this target metric. We just divide it by the optimal shard size, and that's what we're going with. That's the node count. That's the shard count. But obviously, also here, you could implement a different kind of logic. So you might have worked with scaling systems that don't just scale immediately up, but maybe they just add 2 shards, or they only double the shards. And once they come to a certain number of shards, the moment it becomes less shards, they might basically slow down the scale in, because you might be more cautious. You might be saying, well, the last time I did this, it needed 12 shards, and now the calculation is telling me, well, it only needs 6 shards, but I'm not going there yet. I'll still take the 10 shards. I only go down by 2 shards every cycle. So again, lots of considerations on how you can react with scaling. And finally, I talked about the OpenSearch, the law of OpenSearch physics, right? One challenge we still have here is that obviously this has some delay. Essentially, we're calculating a shard count that's not immediately going into effect. It goes faster into effect if the shard count we currently have is too small and we hit the rollover condition of the shard size being finally reached. But otherwise, it will might still take 10, 20, 30 hours before you have a rollover and a different shard size is actually used for that index. And obviously, all the data you have written will kind of suffer under potentially a smaller shard size than you would actually wanted it to have. And it's not natively on OpenSearch, and that might be something we want to change. So currently, you would basically have to run this as an automation script, as a Lambda, as a cron job in Kubernetes, anything you can do in a repeated fashion. There are some solutions. So one of them is maybe sidestep the problem, maybe sidestep the laws of OpenSearch physics completely. So, right, this is a lot of the challenges we have here is based on the idea that you have a node and the node has an attached disk, and this is what you need to work with, and you need to place shards, and you cannot easily move shards around because that also takes time and compute power. So maybe have a completely different architecture, which is more quote-unquote serverless, so something where the compute, the storage, the ingestion, the query part is more decoupled, and you might not even have to consider this problem or the problem changes. And another interesting variation, as we talked about delay, is you might think about having like a kick down feature. So let's say you have this volatile e-commerce app, and that e-commerce app at any point in time might have a hype sale, and suddenly lots of people come to your e-commerce site, and obviously lots of requests create lots of logs, and then something goes wrong. So obviously the app team now needs the bestest query performance ever. So everything becomes more problematic if you don't have a good shard count, right? If you don't have it spread out, you might actually decide for those indexes that you have like this kick down emergency feature where you're saying, well, if suddenly the growth is spiking like that, let my script immediately roll over the index because I want to scale out immediately. I want to be that aggressive on giving this index more room to breathe. And finally, one thing you can basically consider as an add-on for all of that is we now talked a lot about what you can do in one cluster, but obviously you could also apply the strategy across multiple clusters. So sometimes you have this pattern, right, where you have clusters with different amounts of nodes, and depending on what index size you have, you put it on a specific cluster, on your 10, on your 20, on your 30 node cluster, maybe something like that. And obviously you can combine that approach with this automation. So what you do in the end is basically saying, I'm not only making the shard count decision, but with that decision, I also decide on which cluster it lands. And the cool thing you can do there is then, if you use cross-cluster search, and your consumers, your users are actually only getting their data through cross-cluster search, it's completely transparent to them. So they don't know that the next generation of the index actually landed on a different sized cluster. They just search through one unified endpoint, and you do the magic behind the scenes. So that's a little bit more of a deep dive into that approach, and I think here I'll hand over to Aswath to talk a little bit about what we might want to make out of that.
Thank you, Robert. As the last slide, please take the QR code. So basically what we are trying to do with this is, if you like the approach, and if you want it, and you also do not want to do it outside of OpenSearch and want it natively, so we have a feature request. And thanks for John, who pushed us to create this feature request and also named it mutating rollover. So basically, if you look at, at this point, I'm assuming if you're already interested in it, you're probably already using ISM. So the feature request is basically asking for adding a new action. So we have a rollover action. So this is going to be a mutating rollover. So basically, it not only rolls over, but it also adds in the appropriate shard count. Yeah. So basically, whatever we discussed, natively available in OpenSearch. If you like it, go there, put in your +1. If you have a better idea, if you have an improvised idea, if you think, hey, this is nice, but I think there is an even better way to do it, because we want to build the right thing. Yeah. So go in there, add in your comments. If you simply like it, just do a +1, yeah, and that's all that there is, yeah. And that would be the end. So I'm Aswath, he's Robert, and these are our QR codes. Any questions on OpenSearch performance or anything, you can catch us outside. But of course, we have some time for questions, I think. No? Yes? Julia? No? OK. Wow, 40 minutes. OK. OK, thank you. Thank you.